Hi everybody, and welcome to the video for section 12.3. This will be a pretty short video because the section is pretty short. We're going to define one more kind of fractal. As the name suggests here, the twisted Sierpinski gasket. It's basically a Sierpinski gasket but with a twist on it. So it's essentially a generalization of section 12.2. So our construction is a variation of the original Sierpinski gasket, unsurprisingly. For a lack of a better name, we use the word twisted, so this will be a twisted Sierpinski gasket. And the construction starts out just like we did last time. So you start with a seed triangle with three vertices A, B, C. So the next thing we do is exactly what we did last time. You cut out a hole in the middle of the triangle. So you go to the midpoint between C and A and call that N, the midpoint between C and B, call it L, the midpoint between A and B and call that M, and you cut a triangle like this. Now the next move is new. We didn't do this last time. What you do is you just sort of jostle these points a little bit. So imagine a tiny little earthquake comes along and jostles little n to a point n prime, little l to a point l prime, little m to a point m prime. So the direction here is random. So basically like n prime could have been like right here, or maybe right here, but the point is that you just jiggle these these points a little bit. Okay, now you connect n prime, l prime, and m prime. And so this hole right here that connected n, l, and m, it gets twisted so that you just literally drag this point up here to n prime, you drag this point here to l prime, you drag this point right here to m prime, and everything has to follow along. And so when you're done dragging, here's what your figure looks like now. It's sort of a twisted triangle now. All right, so we took something that was a triangle and we dragged the midpoints of that triangle to three separate places, and we ended up with a figure like this. Just like last time, you can now just repeat this procedure for these three blackened triangles here. And that's all we did last time too, right? So what you'll do is, here's the next picture. You'll do the same thing to this triangle, and this triangle. So we'll find the midpoints here, here, and here. We'll cut a hole, and then we'll jostle the hole a little bit. So we'll move the midpoint slightly, and we'll get something that looks like this now. So it's basically, again, it's like the original Sierpinski gasket, but it's been jostled by an earthquake. And then you just keep doing this forever, just like before. So now we have four holes, just like we did before in the Sierpinski gasket. On the next step, we'll have these four holes plus another 1, 2, 3, 4, 5, 6, 7, 8, 9 more holes. So we'll have a total of 13 holes, and so on. So to construct the twisted Sierpinski gasket, you just keep doing this over and over and over again. And here's an example of something you might end up with. And if you squint a little bit, right, if you step back, this looks like a snow-covered mountain. So twisted Sierpinski gaskets are actually used in CGI modeling and creating pictures of, fake pictures of snow-covered mountains, because that's kind of what they look like. So just for example here, this top picture is real. This is a real photograph. This bottom picture was created using a twisted Sierpinski gasket. So again, it's kind of strange. You wouldn't think this sort of thing would be useful, but it does turn out to be useful sometimes, in particular in computer-generated graphics. So here is the summation of how you build this thing. You start with a shaded seed triangle, just like you did with the Sierpinski gasket. And on a given step, whenever you see a shaded triangle, you apply this procedure TSG to it. And procedure TSG means take the triangle, cut a hole in the middle, and then jostle that triangle a little bit. So jostle the midpoints that you chose. The twisted Sierpinski gasket has infinite and universal self-similarity, but because of the randomness involved in the twisting, the self-similarity is only approximate. So when you zoom in, you will see something that looks more or less like the original picture, but won't be exactly the original picture. So for example, this original picture here, this left-hand edge slopes down quite a bit. But if you zoom enough, you see you get a snow-covered mountain again, but this is not sloping down anymore. It's actually going up. So it's not like the Sierpinski gasket in that sense. The original Sierpinski gasket had exact self-similarity. You could zoom in or zoom out as much as you wanted, and you would see the exact same thing. Because of the twisting here and the sort of random earthquaking we're doing at every step, that is not the case here. So it's the approximate self-similarity that gives the shape its natural look, that makes it look like mountains. The original Sierpinski gasket doesn't really look like something you'd see in nature because it's too exact. So this illustrates why randomness is an important element in creating artificial imitations of natural-looking shapes. Natural-looking shapes just aren't exact in the way that the original Sierpinski gasket is exact. But because of the randomness involved in the twisted Sierpinski gasket, you will get pictures that look more or less like things that show up in nature. Okay, so that's it. So the big idea of this section is essentially what we did in 12.2 and 12.1. You start with some sort of beginning picture, and then you apply a recursive process to it. It's just that in this case, the recursive process involves some randomness, some jostling around, so that our final figure did not have exact self-similarity, but it's still a fractal-like figure. Okay, so in the next video we will finish up this chapter by looking at one of the most famous fractal-like figures in computer science and in physics and places like that. It's called the Mandelbrot set.